Exercise 7. So here we have to prove that these extensions don't depend on the order in which the elements are adjoined to the base field F. So we have two parts. In the first part, the number of elements is 2 and the second part is general. Solution part A. Note that the field FB, A by definition is the extension of the field FB obtained by adjoining A to it. And hence FB, A contains both the field FB and A. Naturally, in fact, it is the smallest field containing both FB and A. If you want to use the language of subfields, then you can also call it the smallest subfield containing both FB and A. But subfield of what? For that, you need to remember that in the background there is a field K, of which F, B, A, all of these are parts. Okay, then since FB itself contains both F and B, FB, A contains F, B and A. It has F as a subfield and also it has the elements B and A. Since FA is the smallest field containing both F and A, we have FA contained in FB, A, because this is some field that contains both F and A. It contains B also, but let's forget that for a moment. It contains both F and A, and FA is the smallest field containing both F and A, so it should be contained in this other field. Okay, similarly, since FB, A contains both FA and B, so it will contain the smallest subfield, the smallest field containing both FA and B, which is this, and which according to our standard notation is FA, B. So FB, A contains FA, B. One can similarly show that f b comma a is contained in f a comma b. So they are equal. Although we are writing, one can similarly show that the other inclusion is also true, but truly speaking there is no need for that, because whatever we have proved here has been proved for general A and B. So you can interchange A and B, and that itself will give you the other inclusion. So from symmetry we get this other inclusion and hence the equality. So this is part A. Interchanging two elements in this way does not affect the field extension. Now we prove part B. For this we will apply strong induction on N. We apply strong induction on N. The case n equal to 1 is of course trivial. In that case there is no, you cannot change the order since there is only one element, so there is only one order. So we start our thing with the case n equal to 2. The case n equal to 2 is part A actually. No, we should not. Can we say this, the case n equal to 2 is part A? It's better to instead write this. Has already been proved in part A. Now we will assume our induction hypothesis. Assume that the result is true. For all integers m such that m lies between 2 and n. Where n greater than or equal to 2 is some integer. We will now prove the result for n plus 1. So for that, let I1, I2, In plus 1 be any permutation of this n plus 1 vector. Okay, now two cases will arise. If it happens that In plus 1 is equal to n plus 1, then this is a permutation of I need ink, give me a moment. Okay, so we are saying that if in plus 1 is n plus 1, then the remaining symbols here form a permutation of these symbols obtained by removing n plus 1. That is, if you remove in plus 1 and n plus 1 from these two vectors, then they are permutations of one another. To see why, you can of course think of this situation in terms of bijective function, because that's what a permutation is, but you can more easily see it through this example. Suppose you have this situation where your n plus 1 is 3, so n is 2, and this is your I1, this is your I2, and this is your I3. So there is a bijective map, and the map is like this: 1 gets mapped onto 2, 2 is mapped onto 1, and 3 is unchanged. Okay, so in plus 1 is n plus 1. Now if you remove these two things, then whatever we are left with, that itself is also a permutation of the subset consisting of 1 and 2. So that's what we are saying in this case, and you can pretty much see it's true in general. So because of this, we can now apply the induction hypothesis. So by the induction hypothesis, this extension is equal to the one obtained by changing the positions of the elements like this. Hence, what happens if we now consider the entire thing? Note that this, by the very definition of this notation, is this extension. Is equal to the extension of this extension obtained by adjoining an plus 1. Okay, and this just now we have shown that this is equal to this, so Now instead of writing an plus 1, we are going to write ain plus 1 because they are the same. And this finally is this extension. Oh, sorry, in. So in this special case, we have what we want. Next, assume that in plus 1 is not equal to n plus 1. But since in plus 1 is something from here only, that is because we are talking about a permutation. So it has to be less than n plus 1. Okay. Now for this one we have to put more effort. So what we now do is this. We have okay, should I write by the induction hypothesis? I am now going to change the order of these elements in a particular form, just like what we did here, but not this permutation, something else. It will be better to use to mention that we are using the induction hypothesis. By the induction hypothesis, equal to Fp, where P is the n vector. If you don't want to write n vector, you can write n tuple also, because that's what we are that's what we mean when we say n vector here. P is the n vector obtained from this thing by interchanging an and in plus 1. Okay. Note that because of our assumption, this integer in plus 1 appears here itself somewhere as a suffix of a. So this term is available here as a component, and an of course is also available here. We are interchanging these two. So now in place of an we have ain plus 1, and in place of ain plus 1, which is somewhere inside, we have an, and that n tuple or n vector is p. Okay, and these two things are equal by the induction hypothesis. Since the number of elements is n, so we can change the order of the elements. Okay, now we go to the general one. This is equal to fp an plus 1. I hope this is visible. An plus 1, and that is equal to f q a I n plus 1 a n plus 1, where q is the n minus 1 vector obtained from P by removing ai n plus 1. Now I should explain what this thing means, all of this means. Okay, so the situation now is this. This was our original n tuple, original n vector. Interchanging an and ain plus 1 has given us P, which looks like this. So an has gone inside where originally ain plus 1 was sitting, and ain plus 1 has come from its position and it has taken the position of an. So this is P, and if we remove this, whatever we are left with, where this will end somewhere, that is Q. Since this is not a standard mathematical operation, so I have kept removing within quotes. You can understand what we are talking about here. For example, if you have this 3 vector of 3 objects and you remove C, then you are left with this 2 vector. That's how we obtain Q from P. Okay. Let's keep this. Okay. Now our original extension is equal to this thing, right. Now inside this extension that you see, that again by the very definition of this type of things is equal to the extension obtained by adjoining AIN plus 1 to the field FQ, and outside we have AN plus 1. Now this is this final term is a situation like this. You have a field, you have say B and you have A. So this is nothing but FB comma A. So similarly you have FQ AIN plus 1 comma AN plus 1. Okay, this is just coming, we can write this because of the fact that we have devised the notation like that. It will be better to stop here and mention part A. By part A, the more we progress in our calculations, the more we don't write what we have in the middle. So we start from this, the starting point is always there, and we then write whatever we finally got in the previous calculation. Part A allows us to change this order, interchange these two things. F B comma A is equal to F A comma B. AN plus 1 AIN plus 1. Okay. Now we take AN plus 1 inside. Or in other words, we write what this actually means. It is the extension obtained by first adjoining AN plus 1 to FQ, and then to that adjoining this. The thing we have inside can further be written as Q comma AN plus 1 AIN plus 1. Okay. Now N plus 1 is also I suffix something, because we are talking about a permutation. Say I suffix j, where j is lying between 1 and n. What is the reason for j to lie between 1 and n? Of course j lies between 1 and n plus 1, because those are the available symbols, but j cannot be equal to n plus 1, because see, when j is n plus 1, we have I n plus 1, and this equation would then imply this. But according to our assumption, I n plus 1 is less than n plus 1. In fact, let us mention that note that this, and that's why j cannot be equal to n plus 1. It can be, it is something else, so it will lie between 1 and n inclusive. Thus, by the induction hypothesis, what will now happen to this a n plus 1? We can write f q a, in place of n plus 1 we can write ij. Now this will be equal to f I ai1 ai2 up to ain. The question is, what have we done in this last step? And where have we used the induction hypothesis exactly? In this step, of course, we have actually done nothing other than just using this equation. So in the last step, we seem to have used the induction hypothesis. The induction hypothesis says that when we adjoin n number of elements to the base field F, then we can write them in any order we want. Do we have n elements here? Yes, because Q is an n minus 1 vector, and we have one more element, one more symbol. So we have, this is this thing. Forget about if this thing is an n tuple or an n vector of elements. Okay, but there is one more question. We are writing that this n tuple can be replaced with this n tuple where the symbols are this, starting from I1 ending with IN. Do we have all these things here in this n tuple? That is the question. Ij, of course, is here. We can see that. What else is there? There is a problem if we have this here somewhere, but it's not, no wait, what I am saying is not actually this. There will be a problem if we have ain plus 1 here in this n tuple, in this n vector. Is that possible? No, that is not possible, because ain plus 1 has already gone outside. So whatever ai star we have in this n tuple, that is for star lying between 1 and n. And in fact we have all of them, because this is an n tuple and the indices are, I mean, we are dealing with a permutation, so there is no repetition of indices, so there is no fear of losing any index, or there is no fear of gaining any foreign index from outside. All the indices that we have between 1 and n are already present here, and they are appearing in the form I star, I suffix star. In plus 1 has gone outside, so we in fact have everything that we have here in some other order, and that order can be changed, and in its place we can write this. That's where we have used the induction hypothesis. So now everything is clear. Hence, so we start our calculation still starts from here. This is equal to this fq comma an plus 1 ai n plus 1, and this is equal to this. So this finally completes the induction. And proves the result. So from now on we can interchange the order of the elements that we are adjoining to the base field in any way we want. After this, we have exercise 8. If the elements A and B belonging to K are algebraic over F, of degrees m and n respectively, and if m and n are relatively prime, prove that f a comma b is of degree mn equal to mn over f. We already know from what is that result, I think it is theorem 513. We already know that, okay, do we know this, or I don't think, but I was going to say actually that is not true. It will have to be proved. It does not follow directly from a theorem. I was going to say that the degree of this extension over f is at most mn. Okay, so we have our field f and some extension k of f, and two elements a and b in k are given, and it's given that both of them are algebraic over f with degrees m and n respectively. Additionally, it's given that the integers m and n are relatively prime. Then we have to prove that this extension has degree mn over f. Okay, so let us see the solution. So we start by considering the extension that we obtain when we adjoin just a to f by theorem 513. We know that this degree, the degree of fa over f, is equal to m. In fact, that's what an element having degree over f means, that this degree of the extension obtained by adjoining a to f over f is equal to m. Since B is algebraic over f of degree, we should mention that algebraic of degree n over f, B is at most n over f a. What have we written in this sentence? Since B is algebraic of degree n over f, that is given, we are saying that B must be algebraic of degree at most n over fa. What is this? See, B is algebraic of degree n over f if the minimal polynomial over f of B has degree n. Okay, so suppose that minimal polynomial looks like this. Plus alpha n, where the alpha i's all belong to f. This is the minimal polynomial of B over f. Over f, that is that this containments, these things express. So that means what? If we substitute B for x, then we get 0, and no polynomial of smaller degree means no non-zero polynomial of smaller degree can make will be satisfied by B. Okay, now note that since f is contained in fa and all the alpha i's are in f, so all the alpha i's are automatically also in fa. So this, besides being a polynomial over f, is also a polynomial over fa that B satisfies. Now it may or may not happen that over fa there is a smaller degree polynomial which also B satisfies. In any event, the degree of B over Fa will be less than or equal to n. If this is the smallest degree polynomial over Fa that B satisfies, then the degree of B over Fa will also be equal to n. Otherwise, if we find a smaller degree polynomial over Fa that B satisfies, then the degree of B will decrease. Over F, this is the minimum possible degree, but over Fa, since more scalars are available, maybe we get a polynomial of smaller degree that is satisfied by B. So that's why we are saying B is algebraic of degree at most n, that is degree of B over Fa is less than or equal to n. And hence, by theorem 513, again the degree of this extension over Fa, which is equal to this degree is equal to the degree of B over Fa, that is at most n, less than or equal to n. Now, by theorem, is the first one theorem or lemma? Theorem 511, degree of this extension over F, we know that this is equal to the product of the degree of Fa comma B over Fa times the degree of Fa over F. Now the first factor is less than or equal to n, and the second factor is equal to m. Okay, so we get this thing, that this degree we want to prove it is equal to mn, but we have shown that it's less than or equal to mn. Now, okay, now what? Now, since Fa comma B contains Fa and Fa comma B, which is equal to F B comma A by the previous exercise, contains Fb as vector spaces over F, both Fa and Fb are subspaces of Fa comma B. because they are subfields, so they are subspaces, and they, it's obvious that both FA and FB contain F. So these three things are vector spaces over F, and these two are subspaces of the larger one. Okay, so thus by the corollary to the first theorem, the dimensions of these subspaces will divide the dimension of the original space. The dimension of the first one, this one, is M over F, of course. This divides this, and just like that, the dimension of FB over F divides this. Now we use the hypothesis that M and N are relatively prime. Since M and N are relatively prime, we have Mn dividing this dimension or the degree, and hence Mn must be less than or equal to this degree. So now you combine these two inequalities. Thus finally we have equality. So it means that, for example, A is an element in K of degree 3 over F and B is an element of degree 2 over F. Then this extension will be of degree 6 over F, because 2 and 3 are relatively prime. In fact, they are prime also. We don't really need M and N themselves to be prime, just relative primality is enough. And let us now see another one, exercise 9. Whatever we have done with these things, extensions, their degrees and everything, they can now be used to say some things about finite fields, which we mentioned earlier also. Suppose that F is a field having a finite number of elements. Q. The cardinality of F is Q, which is some positive integer. Part A. Prove that there is a prime number P such that if you consider this sum where we take the same element and we take it P times, then this sum is equal to 0 for every element in F. Part B, prove that Q is equal to P to the power n for some integer n. Part C, if A belongs to F, then A to the power Q is equal to A. Part D, if B belongs to K, where K of course is some extension of F, and this is algebraic over F, prove that B to the power Q to the power M is equal to B for some positive integer M. Okay, so in a finite field these things will happen. So let's go through the parts one by one. Part A, prove that there is a prime number P such that so in the beginning itself we can use the additive group structure of the field, since F is a group under addition we have Q times this is equal to QA is equal to 0, and here we have used by the second corollary to Lagrange's theorem. It has a name, so we can refer to the name corollary to theorem number 241, that is nothing but Lagrange's theorem. So what we have done here is this. This is a group, we know, in fact it's an abelian group, although we don't need commutativity of the group structure here. Okay, now that means what? And the order of this group is Q. So if we take any group element, then this corollary to theorem 241 implies a to the power q is identity, which is this, that corollary. Now, since we are in an abelian group and our operation is addition, so a to the power q is written as qa, which is a q times, which in the additive notation is a plus a, so that is qa, and the identity element here is 0, the 0 element in the field, so this is equal to 0. But now let us again remember that we are in a field. So in a field, when this happens, the characteristic of the field is finite, or the field has finite characteristic. So we can write like this: hence f is of finite characteristic. These things we saw in our study of rings, and there itself we proved this other result. It then follows from exercise 6 of section 3.2 that this characteristic is a prime number. Prime number P. Thus, by the definition of characteristic of a field, or in fact we defined it for an integral domain. Thus, P times is equal to 0, and P is the smallest positive integer. According to the definition of the characteristic, P is the smallest positive integer for which this is true for all A belonging to F. So that is part A, and here we see that this P is nothing but the characteristic of the field. Okay, then in part B we have to prove that this number q, which is the number of elements in the field, must be an integral power of p. That is, q must be a number which has only one prime factor, that is p. It cannot have any other prime factor than p. So to prove part B, we will suppose just that there is some other prime factor. Suppose there is a prime r not equal to p such that r also divides q, just like p. R also divides, and in this entire thing p of course divides q. That follows from ring theory itself. I mean, whatever we did there with characteristic, there itself you can see that. Okay, now again we are in the additive group F, whose order is Q and R is F prime that divides Q, and we have the Cauchy's theorem for abelian groups, because now our group is abelian also, since F is an under addition Cauchy's theorem for abelian groups implies there exists some element B belonging to F such that B is not equal to 0 and RB is equal to 0. Recall Cauchy's theorem for abelian groups. You have an abelian group G and order of G is something, a finite abelian group in fact, and order of G is divisible by some prime R. Then you can find an element A in G which is not equal to the identity element and such that the power A to the power R is equal to identity. In place of G we now have this abelian group, and in place of order of G we have Q. So in place of A we have chosen B. B not being identity in this group means B not being 0, and RB means B to the power R, written in additive notation. So RB must be equal to identity which is 0. Okay. Since P and R are relatively prime, since their GCD is 1, there exist integers alpha and beta such that 1 is equal to P alpha plus R beta. Now B is equal to 1B, which is equal to, let me just write the calculation down, then I will justify the steps. P alpha plus R beta B, this is equal to alpha times PB plus beta times RB. This is equal to 0 plus 0 equal to 0. A contradiction. What have we contradicted? We have contradicted this. We have obtained B equal to 0, but B is not equal to 0. Now, instead of saying what each step means, I am going to redo the calculation as if we are in a general group, not the additive group in the field. In the general group, this same calculation will look like this. by the rules of exponents. So whatever we have written here is group theoretic, and these are actually integral powers, but since we are using additive notation, our operation is written additively, so we are writing things like this. It may be somewhat difficult to understand this at first, but think of them in the additive group in the field and things become clear. Okay, so we have got a contradiction. That means our supposition is wrong. So our supposition is wrong. That is, P is the only prime divisor of Q. Q equal to P to the power n for some positive integer n. Why positive integer? Why not non-negative? What happens when we take n equal to 0? Then the number of elements in the field is 1. There is no field with one element. That is because, you see, if you have only one element in a field, some element, then that is the 0 element, and so according to the definition of a field, the non-zero elements in the field should form a multiplicative group that is abelian. Now, since the only element here is 0, the set of non-zero elements in this field is empty. So how can it be a group? So every field has at least 2 elements, and in particular in a field 0 and 1 are different. Okay, so this n cannot be 0, it has to be positive. So that's why n is a positive integer. Okay, so this is part B. Then in part C, what we have, if A belongs to F, then A to the power Q is equal to A. If A is equal to 0, then obviously this. Now this A to the power Q is the product of A with itself Q times using the multiplication in the field. Okay, in this equation the additive group structure is not there. If A is not equal to 0, then A belongs to the set consisting of all the non-zero elements in the field. Since this set is a group under multiplication, and the order of this group is one element less than the number of elements in the field. Corollary to the theorem 241 implies a to the power q minus 1 equal to the identity element in this group. In this group, in the multiplicative group, the identity element is the unit element in the field. Hence, so for a zero element also this is true for the zero element, and for any non-zero element also this is true. So this in general is true. And finally part D. So in part D it's given that B in K is algebraic over F. Then we have to prove this for some positive integer m. For this one also we consider two cases, namely when b is 0 and the other when b is non-zero. For b equal to 0, we have b to the power q to the power 1. This will be 0 and that is equal to b. So in place of m we can choose 1, and in fact you can see that any positive integer m can be chosen in this particular case. Assume b to be non-zero. Okay. Since b is algebraic over f, it is, or it has a minimal polynomial. Minimal polynomial in fx of degree m. For some positive integer m. Okay. We haven't Okay, then theorem 513, you go to that theorem and you look at its proof, you will see this thing. Implies every element of K is of this form, beta naught plus beta 1b etc. plus beta m minus 1 b to the power m minus 1, where beta I belongs to F for I lying between 0 and m minus 1. Algebraicity of B over K allows us to have this, to express all the elements in K as linear combinations of powers of B, that to this many powers, m powers. Okay, so all the elements of K are of this form. Now any element of K is of this form, so that means the elements of K can be obtained by changing the beta i's in this expression, because in this expression, which is a polynomial expression in B, the powers of B are fixed. The only things you can change are these coefficients or the field elements. Now since F has how many elements? Q elements. It follows that K has Q to the power m elements. In fact, in theorem 513, what is it that we proved in theorem 513? Theorem 513 says, one half of the theorem says that these powers of B, this is a basis of FB over F. Okay, wait, are we getting what we want here? K is an extension of F, and theorem 513 says that this is a basis of FB over F. It does not say that this is a basis of K over F. Oh, because K may be larger than FB, no? K may be larger than FB. Oh, but then what is the okay. Now if we don't use k here, of course what I have written here is not correct. I should write fb here. All the elements in that extension looks like this. So that means I have to replace k with fb, but the thing is, can I get the solution by using fb in place of k? Let me see. So fb has q to the power m elements. Yes, there is no need to consider k. K is just there in the background. I mean, k is the thing where everything is, k is the place where everything is happening. Okay. Yes. Since b is not equal to 0, b belongs to the set fb minus 0, which is a group under multiplication and has order. So we have just removed one element, so it has order q to the power m minus 1, and b of course is in fb. Note that b is not necessarily in f, b is an element in k, the extension. So by again that corollary, due to Lagrange's theorem, we have b to the power, the order of the group is equal to the identity element, which is 1. Thus b to the power q to the power m is equal to b. So that's what we wanted to show, I think, in this part. Yes, and we now know what this positive integer m is. It is the degree of b over f. So this completes the solution. After this also there are some exercises where we will deal with the notion of algebraic numbers, which, if you recall, are complex numbers that are algebraic over the field of rational numbers. So those things we will see. So this we will do in the next video. So if you want to comment on these things, you can write in the comment section below, or you can mail me at the usual address. So until the next video, this is me, Lucifer, from a mathematical room. Have a nice night.